My name is Gopa Kumar. I am representing National Federation of Engineers for Electrical Safety. We are an engineers association, or very recently started. We have here a founding member, Mr. Saliji is sitting here. We 12 engineers together founded this organization. We have about 1,000 members all around India, and we have about 28,000 engineers following our training programs. First of all, I would like to say thanks for ECAM and all the organizers, all the management of ECAM to invite me to this program. I would like to introduce a little bit about NEC, National Electrical Code of India. Not all the points, but some important subjects. But before that, I would like also to invite Mr. Ullas Vajre. My language is very, other than English and Tamil and Malayalam, other languages are, very difficult for me. I would like to invite Mr. Ullas Vajre to just have a small introduction about the NEC and what NFE is doing. Mr. Ullas Vajre is a member of ECAM, also a very supportive member for NFE. Please, sir.
नमस्कार. मित्रो, आपण बघतोय की आपल्या देशात दिवसेंदिवस कुठे ना कुठेतरी विद्युत अपघात घडत आहेत. यामुळे मनुष्य आणि मालमत्ता हानी या सर्वांची एक गंभीर चिंता निर्माण झालेली आहे. जरी प्रशासनाने नियम व कायदे केलेले आहेत, तरी विद्युत धोक्यांपासून सर्वांनी मिळून प्रशासनाला पाठिंबा देणे आवश्यक आहे. ही परिस्थिती लक्षात घेऊन नॅशनल फेडरेशन ऑफ इंजिनियर्स फॉर इलेक्ट्रिकल सेफ्टी म्हणजे NFE यांनी राष्ट्रीय स्तरावर विद्युत अपघातात निर्मूलनाच्या उदात्त हेतूसाठी समविचारी लोकांना एकत्र आणले आहे. NFE विशिष्ट प्रशिक्षण आणि प्रमाणपत्र कार्यक्रमांद्वारे डिझायनर त्यांनी एक स्कीम चालू करणार आहेत की ज्याच्यामुळे की डिझायनर्स दे विल बी सर्टिफाईड डिझायनर, सर्टिफाईड कॉन्ट्रॅक्टर्स आणि सर्टिफाईड व्हॉट यू कॉल इट इज कन्स्ट्रक्टर और सुपरवायझर्स. सो अशा 3 कॅटेगरी त्यांनी केलेल्या आहेत की ज्याच्यामुळे हे सर्टिफिकेशनची प्रोसेस पूर्ण होणार आहे आणि आपल्याला चांगले कार्य करणारी लोक मिळणार आहेत त्यातनं. तर असं हे NEC बद्दल मी थोडक्यात संपवतो माझं बोलणं. धन्यवाद.
Thank you very much. So I would like to make a small correction. It's not certified contractor or certified engineer or something like that. Globally, an electrical engineer, you must have heard of chartered engineer, means there is an ISO standard system, ISO 17024, which makes guideline how to certify a person, like NABL accredited laboratory as per ISO 17025. So we are trying to make a scheme for certifying personnel. So we make the rule, and that job is working on. Now anyway, coming back to the presentation, in 2023 we had two important documents are being published by the Central Electricity Authority as well as the Bureau of Indian Standards. Of course, 3 documents. One more document is published by BIS, which is IS 18732. The first one by CEA is CEA Regulation 2023. Then BIS, the NEC was published also in 2023. Basically, all these standards together are going to make lot of change. Often engineers say that we are trying to make trouble in the market. Please note that these documents are not to create a trouble. These are to increase the safety system or safety in our country. For example, all of you know that 2047 India wanted to become a developed nation. But if you look at the electrical safety scenario, for example in Mumbai, fire brigade says 80% fire accidents are due to electricity. I'm sure all of you are aware. Am I correct? We have a lot of young students. Are you aware that 80% fire accidents in Mumbai are due to electricity? Yeah. Is it true? Nobody knows. Nobody knows. Electrical engineers, we can refuse that. No, it is not due to electricity. Fire is not due to. But what is the proof? Now then we check, okay, the standards are written, these many safety measures, are these safety measures are included in the building? Then the question starts. Now anyway, Please note that out of 100 accidents happening, about 50 accidents, 50% are happening within the consumer premise. About 48% happens within the low voltage electrical distribution, low voltage plus medium voltage, up to 33 kV. That means the overhead lines are creating some of the accident and majority are within the building. So our focus is mainly towards this voltage, because if we educate the practicing engineer about this subject, lot of improvement is possible. Now, if we look at the global statistics, this slide is from a presentation by a Japanese delegation in 2016, which was actually an eye-opener to the government. 723 people out of 100 million population are getting killed due to electrocution in India. 723 out of 100 million population. If you look at Germany, it is something about 87 or 67. Now in UK, it's about 45. In Japan, about 12. So in comparison to Japan, 12 people die out of 100 million population per year due to shock. India, 723. So you can find out how many multiple times we are. Even in USA, it's about 124 or 125. Now, for example, if we look at the actual accident reporting system, our reporting system is also not that efficient like most of the foreign countries. The same Japanese delegation, they have presented that they made a survey, and the survey reports are, you can see here, the electrical safety system in India, scenario in India, especially in houses, industries. That means after the meter board, after the point of commencement of supply. So the electricity supply company is giving up to the distribution board, up to the meter, and after the meter, our safety score is 16%. In comparison, you can see the other countries. So if we go in this fashion, of course, we will not be able to reach the goals of the government like sustainability goals as well as the development goals. It's very difficult because on one side, we keep on developing, new technologies are going into come, consumers are becoming prosumers, EV is going to come, and a lot of revolution is already happening, and we have to be a part of this one. And we cannot afford to have the accidents like this one. The first one on the left side, what you are seeing is an accident in a operation theater in a hospital. So here you can see a small electrical item, nothing but a ventilator which is supposed to save the life of a person, is catching fire, which is there on the left side video. On the right side, an air conditioner is catching fire, and this fire has killed about 17 people. So the second one on the bottom, 17, and the first one, you can see the fire started. You can see it clearly. See, the electrical apparatus is catching fire. The question we need to ask is why? What happened? Why this device is supposed to, these are, for example, life-saving equipment. It is supposed to save the life of a person, not to kill. Why this device is catching fire, and what happened to its fuse? Why the MCB didn't trip? So the first question we should ask is, why the protective device is not tripping and it is becoming a fire? And this is not acceptable. Now, what others are doing, why the other countries are able to make a very good electrical, or their safety scenario is much above us. If we look in that way, the low voltage electrical installation, we say low voltage means up to 1000 volt AC, 1500 volt DC. Globally, all around the world, the same standards are used, made by IEC TC64. The standard is called as IEC 60364. In India, the same standard is adopted as IS 732 up to some of the chapters of the same IEC, then NEC. So overall, the entire international standards followed in America for making safe buildings in America, followed in UK to make their electrical installation, followed in Germany, followed in France, Italy, all over the globe. The same document is also existing in India, which is called as NEC, National Electrical Code of India. The latest one was published in 2023, January. This particular document explains about design, erection and testing of an electrical installation. In fact, testing is not the correct word, verification is the word. NEC is not a product standard. It do not talks anything about a product like wire, what quality of wire, what quality of switch, what quality of MCB. That is the problem of the product manufacturer. That is the product standard, whereas NEC is an installation standard. So that means we also have the same standard which is equal to the globe. Then why so much accidents are happening? We have to actually analyze a little bit about the electrical, the regulatory part of our system, the legal system. Now our legal system, you can see on the top, we have the Electricity Act, which is enacted in the Parliament. The Parliament passes Electricity Act. The latest one is the Electricity Act 2003. Provisions of the Electricity Act give power to the Power Ministry or gives power to the government to make Central Electricity Authority, and the Central Electricity Authority is authorized to make regulations to make safe installation. So the second one is regulation. The latest regulation is Central Electricity Authority measures relating to safety and electric supply regulations 2023. This is the second legal requirement. Now, a regulation will contain subjects related to generation, transmission, distribution, and so many things. Majority, the regulation talks about the safety up to the point of commencement of supply. That means generation, transmission, up to the meter board. Inside the meter board, we have to follow, or within the consumer premise, we have to follow the code of practices such as NEC, NBC, and so on. Then, if you wanted to make a good electrical installation following the code of practice, you need to have products, and products are guided by the product standards. Then you have the operational documents. This is basically the hierarchy of electrical safety. Now, if we look at the regulation, what happens? So, why so much accidents are happening? What is the real reason? If we look at the regulation point of view, we had the electricity regulation 1937. Or electricity rule. This electricity rule was changed to IE rule, Indian electricity rule. Oh, sorry, I thought somebody is there. Okay. The Indian electricity rule in 1956, which is changed to CEA, Central Electricity Authority regulations during 2010. Now that particular 2010 regulation was also changed to 2023 regulation. One of the important subject which every person who is involved in electricity should understand is, please listen. The final regulation was published on June 8, 2023. That means June 7, 2023, the 2010 regulation was followed. Whatever written in 2010 regulation about the low voltage electrical safety, the guidelines was actually from 1937. There was no improvement from 1937 up to 2023 basically. But there was no mistake, the wordings were perfect, but the legality, each of the regulation was too complicated. So it was very difficult for an electrical engineer to read and understand. Now in the new regulation, the wordings are very much simplified. As a result, it's very easy for the engineer to read. So basically, regulations mainly concentrate up to the point of commencement of supply. After the point of commencement of supply, regulation 14, sub-regulation number 2 applies, where you can see the regulation 14, sub-regulation 2. Save otherwise provided in these regulations, the relevant standard including National Electrical Code of India shall be followed. For the first time in our country, the regulation is using a word shall. Shall be followed means mandatory. It must be followed. Until now, 2010 regulation, the wording was may be followed. National Electrical Code may be followed. May is a recommendation. May means you can follow. If you want to, you follow. Otherwise, still okay. May has been changed to shall, which is going to bring lot of change. The third one, materials and apparatus used shall conform to the relevant standard. Relevant standard is nothing but the IS standard. If there is no IS standard, IEC standard we should follow. So basically, for the first time after 75 years, the code of practice is made mandatory in the regulation. I will just take you to few of the code of practices, few of the regulation. I don't want to explain, all the regulation. It takes a lot of time. One of the regulation which is very favorite to me, this is about earthing, for example, which is a very confusing subject all over India. So now the regulation says every building shall have protective equipotential bonding by interconnecting exposed and extraneous conductive parts in the as per the relevant standard. Earlier, it was in a different style. Now, it is made very simple. What does it mean? Your building has got a lot of metal parts, dead metal parts, I would say. Dead metal parts in the sense, metallic parts, maybe the casing of a class 1 electrical apparatus, or maybe the metal structure, something like this. We have the air conditioner duct, we have the metal, the metal columns. Every building shall have an equipotential bonding, means all the dead metal parts must be interconnected in such a way that simultaneously accessible metallic parts doesn't have a shock voltage. The first safety measure, protection against shock, is this one. That means in any building, it can be residential or industrial or multi-storied, whatever, every building, the building has to be divided into several locations, and depending upon the size of the building, each of the location shall have this kind of a equipotential bonding. This is what is written in the regulation. As I said, 1937 also this was there, but the reading was different. This time the regulation made it crystal clear. So this is one of the change. Like this, I can tell you maybe 100 changes came in these two documents. One of them, the second one, have fault loop impedance. Fault loop impedance, generally, if you look at the red one, which was the old regulation, limit earth resistance sufficiently low. So the old concept was, you have something in soil and you have an electrode. Now if you reduce the resistance of this electrode, you will achieve something. This has been removed. This earth electrode resistance has been removed in the standard few decades back, very old, but in the regulation also now it has been changed. The earth fault loop impedance came into picture, and a lot of, like this changes has happened in the regulation. Electrical safety sometimes is a very simple subject. We should think what we use. For example, a plug and socket. You know very well that Indian plug and socket, round 3 pin, 5 amps, 6 amps, 16 amps, there are two types. These are the Indian plug and socket. But practically if we look at most of the time, the plug and socket which we use, I'm sure this is a British, the first one on the left side is a British socket, British plug. Then you have the Schuko plug, Schuko socket. Most of the time, the electrical appliance which we buy from the market, it comes with a different plug. Then we try to put this plug into our Indian socket. Sometime, if you had a good breakfast, it will go inside. You have to press a little bit. But while pushing, it goes inside and it works. But once when you try to pull it out, 2 times it will come. 3rd time the whole thing is broken. Then what do we do? We take a cello tape and put above, a red color tape above the socket. Will it work? No, it's a violation. First of all, we should not allow sale. The government should not allow sale of such products in India. Every product made in India, as per the Indian standard, should come with an Indian plug and socket. Do you think that a company or somebody in London use a product with the Indian plug? This will never happen. Only in India. Why do we allow so many other countries' devices to come in? Second item, second photo, what you are seeing is an iron box. It's a 2000 watts iron box and with a 6 amps plug. Any electrical apparatus more than 1000 watts should have a 16 amps plug. Whereas this one is 6 amps, because 6 amps, the current is more, you cannot handle it. So such violations are quite common in our country, very, very common. Even the expert electrical engineer will not look into these subjects seriously. For example, if you go to any of the 5-star hotels in Mumbai, every year these 5-star hotels are making electrical safety audit. If you look at the plug and socket which they use for their water heater, the kettle, the iron box, these are used. It's a violation, clear violation. Similarly, another subject, I'm sure some of you may be knowing this kind of a picture. This is a bus bar, the tap of box in a bus bar. Terminals are so small and we use large size wires. Then we have a habit of twisting the wire inside the box. As a result, what happens? This installation, which is supposed to work for 25-30 years without trouble, not even it will work for 2 years. It will, unnecessarily, it will heat up. Then what do? We take thermography and try to tight every electrical, every joint. This is against electrical safety. This is not electrical safety. So such changes are there in NEC. NEC, National Electrical Code of India, now it is a mandatory requirement. The first one, NEC, came in 1985, second edition came in 2011, and then now we have the third edition, 2023. We have 3 members, not 3, 4 or 5 members sitting in the hall, those who are in the committee drafting this particular NEC. We have Saliji, we have Amol, also we have Mr. Ullas Bajare, we are all there in the committee drafting this particular standard. First of all, for electrical products, you have so many product standards. For each and every product, there is a product standard, such as wires, plug-and sockets, or your MCBs, MCCBs, RCBOs, motors, cable trays, trunking. There are product standard. And who is responsible for this product standard? Product standard is the headache of the manufacturer of that product. He has to design, he has to provide the product which is conforming to the standard. Means he has to make it, he has to test it, and he has to supply the goods in the market, and he has to comply to the standard. This is not the headache of a contractor or a designer or an auditor. This is the product standards are the headache of the manufacturer. Then what is the problem with, what is the headache of the contractor or the designer? The whole electrical installation, starting from the transformer terminal up to the last socket and the connected devices. So NEC is the standard which explains selection, erection, verification of the entire electrical installation, mainly focused on safety. So it covers normal installation, it covers special electrical installations such as bathrooms, swimming pools, then medical location in hospitals and so on. It also talks about DG, UPS, solar PV, also power quality, energy conservation, lightning protection. So basically, all the electrical requirements in a building are explained in NEC. If you wanted to, let us say you wanted to design a circuit, then you can go to NEC, you can find out, what kind of load, how to select the wire, what is the size of the wire, how to route the conduit, how to select the switch. So all these information are there in NEC. So more than 100 experts working in this particular group, and last 4-5 years we were working to make this particular standard. NEC, for example, it consists of 8 chapters, part 1 to part 8. Part 1 has got 22 sessions, each talking about a typical subject. Say, for example, part 9 talks about wiring system, part 10 talks about shock protection, part 11 thermal effect means fire, part 12 overcurrent, part 13 fault current, EMI, electromagnetic over voltage and electromagnetic influences, and so on. So there is this up to 22 sessions of part 1 talks about general electrical installation. Similarly, part 3 talks about special electrical installation. You can find out some of the special installations, starting with the domestic dwelling, what you should do in a house, for example, medical location, exhibitions, furniture, and so on. So basically, this is what is there in NEC. I will just take you to I think I have few more minutes. So I will take you to some important contents of NEC. As I said, if we explain maybe 2-3 days, I can explain hundreds of examples which has made a change. I cannot make all the changes, but I cannot explain all the changes. I will try to explain 1 or 2. So basically, every electrical installation need protection against shock, protection from thermal effect means heat arcing, overcurrent and fault current, and voltage disturbance. These are the 4 fundamental requirements of electrical safety in every electrical installation. The idea is nobody should get shock, no fire from the electrical installation, no overcurrent, because overcurrent or short circuit current will create again sometime thermal effect or sometime electromechanical forces, and voltage disturbances. This is, this part probably it looks like a theory, but once when we go into it, it becomes more and more complicated. For example, protective measure against shock. It is classified into basic protection, fault protection. Basic protection, there are different methods: insulation of live parts, enclosures, obstacles, placing out of reach. Fault protection means, there is a good electrical installation, but there is a fault. During fault, what you should do, I explain it with a picture, for example, here. So the first one, what you are seeing is there is no basic protection, means a live part anybody can touch a live part and get electrocuted. Means no basic protection. An idea of basic protection is you put live parts inside an enclosure. As a result, nobody goes and touches the live part directly. You get basic protection. This is one idea. Like that, several ideas are there. Then if there is a fault in that particular panel board, for example, then the person gets shocked. What do? Implement fault protective measure. So you need basic protection, you need fault protection. Basic protection, there are several measures. Fault protection, there are several measures. Then we need enhanced protection, sometimes, both, a much stronger protective measure and additional protection. So basically, this is the concept of shock protection. But once when we go deep into it, sometimes this subject alone we need to understand very deep to implement or to design an electrical installation. The fundamental, for example, fault protection by protective equipotential bonding and automatic disconnection of supply. Fault protection means shock protection against shock, say for example. So protective equipotential bonding means you know this very well. Every building, all dead, simultaneously accessible metallic parts should be interconnected in such a way that there is no shock voltage. That is the first safety measure. But what do? We make this, instead of interconnection, we put each and every part of the electrical installation, because the word earth, people are confused and we think that earth means the soil. We put a transformer neutral 2 numbers into soil in a plate, then body 2 numbers into a GI pipe, and we make hundreds of earth electrodes in soil. Unfortunately, this was never written in any standard or any regulation. The second one, sometimes we make, separate lightning protection, separate power separate, then clean separate, electronics separate. This is also a big mistake. This is also not written anywhere in the standard. So this is not the way of earthing. In fact, in IS 732, which is again the IEC standard, I show you a wording in IS 732. You can read this particular clause 5.4.2.1 to 1.2. Where provided, that means if provided, earth electrode within an installation shall be connected to the main earthing terminal of that installation. You have a common bus bar. If you have earth electrode, you connect to that bus bar. That's it. And then there is a note, an installation does not need to have its own earth electrode. An installation means a building, let's say a hospital, does not need to have its own earth electrode is what is written. That means your hospital don't need to have an earth electrode. So, but you need to have a very good equipotential bonding. The protection for safety or protection against shock, the fault protection, we say fault protection by protective equipotential bonding and automatic disconnection of supply. Automatic disconnection means the protective device should trip within certain time. It is not like, your MCB can trip after a few seconds. No. For example, on the final circuit, if you look at a TN system, 0.4 second, within 400 millisecond, the protective device should trip. In case of TT system, 0.2 second, within 200 millisecond, the device should trip. And if the device is tripping within this time, there is no fire, there is no shock. So basically, having a protective device is not important. Having a protective device which is doing its job, it has to trip. That is much more important. I have investigated several fire accidents as well as shock accidents. 90% cases, the protective devices are so strong. What I mean is the protective devices are there, but it is so strong. It is not able to trip due to several reasons. Sometimes dust, sometimes oversized, sometimes no testing, there is no return path. Several reasons are there. Basically, electrical safety engineer should ensure that equipotential bonding and disconnection of these devices, the devices within this time is very important. Then if you wanted to make that, then we go to the system earthing like TNC, TNS, TT, TNCS and all. Now I explain you what exactly I am meaning. For example, you have devices to trip such as MCB, fuses, MCCBs. I am showing you a TNS system. The definition of TNS system is source, the current carrying, one of the current carrying conductor is earthed. exposed conductive parts of the installation, means metal body of the installation, are connected back to the neutral, the earthed point of the source through a separate conductor. Means your panel board connected back to the neutral through a separate conductor. Very simple definition is there in the, you can see the definition here. This is from IS 3043. TN system has one or more point of the source of energy directly earthed, and the exposed and extraneous conductive part of the installation are connected by means of protective conductor to the earthed point of the source. That is, there is a metallic path for earth fault current to flow from the installation to the earthed point of the source. There is a metal fault return path. Then only your MCB will trip. So that is what is shown here. Now there is a fault. The fault current will circulate in this loop. The impedance of the loop decide the amount of current, and the amount of current decide the disconnection time. Very simple. The impedance of the circuit decide the amount of current. The amount of current decide the disconnection time, because each and every the device have its own tripping characteristics. For example, MCB, type C MCB, instantaneous tripping, it needed 10 times the rated current. So a 63 amps MCB, if the current is 10 times, means 630 or more than 630, then only it will trip in 200 milliseconds. So what we should do? Our electrical installation should be made in such a way that during fault of negligible impedance, the minimum current which is flowing through that MCB should be more than 630 amps. That is what it is. So the calculations are given here. In NEC, we have also included a table which talks about the impedances. So if you look in detail, fault loop impedance shall be calculated during design, it has to be verified during erection, it has to be tested during audits, and so on. A very important subject. Now, important point what I wanted to tell you is not only the National Electrical Code, but the regulation, Central Electricity Authority regulation, which is followed generally by the Electrical Inspectorate. They also have written very clearly. So in future, electrical inspectors will start asking you, you show me the test report, you show me the fault loop impedance test report. This is going to come. This picture, I just put it from IS 3043. This explains how to make an earthing of a DG and mains changeover. You have a common bus bar. You connect all dead metal parts to the common bus bar. Neutral also you connect to the same bus bar through a link. That is what is required. So these information were existing in the standard for a longer time. Let me go back. Also, when we talk about the last part, NEC talks about design, selection, erection, verification. The last part is verification. People always say energy audit. But audit, you see, with respect to electricity, there are different kind of audits. Energy audit, which is the primary subject, is to talk about the conservation. Use devices or save energy is the main target. Power quality has got its own requirement. Safety audit. Most of the time, safety audits are also carried out in several of the installation, but so far, this fault loop impedance test or the other test was not common. So, we didn't use the word audit in our standards. We use the word verification, because audit is a subject where, imagine you have 100 circuits. 10 circuits you test and you imagine that the rest 90 is in a good condition. That is audit. Audit is not used. Here verification, we are talking about safety. If there is no safety, building can catch fire or people will die. Every circuit you should do. So you should verify. Verification consists of inspection. There are several subjects of inspection. You can go to part 1, section 17 of the inspection. In fact, Mr. Sanjay Koladkar was the person who has drafted this particular part. He is a member of ECAM. I don't know whether he is here or not. I didn't see him. So these 17 parts, 17 or 19 inspection is required, which is, it is not invented by us. It is from the IEC standard. We just copied and pasted it, that's all. Then, for example, the first inspection is method of protection against electric shock. I will just show the picture just to make you understand that electrical safety is not a simple subject. It's a complicated subject. You need a lot of skill to do it. For example, the first one, protection against electric shock. Protection against electric shock is achieved by these many measures. Depending upon the location, say for example solar PV, you have to adopt double insulation. Let's say a furnace, you have to adopt another method. depending upon the location, you have to understand what is the safety measure and where it is applied, and the first inspection itself is to check the location whether these measures are implemented properly. Like this, there are 19 inspection measures. I am sure India will take at least the next 10 years to learn about this completely, because these are from the IEC standard. Most of the developed nations were following it since 40-50 years. So during this 40-50 years, they learned a lot. They know what to do, whereas in our case, we will take time to learn about it. Then inspection followed by testing. There are 10 testings plus 11th, which is a pad test. The 10 tests ensure that your building is in very good shape. It is electrically safe. The 11th one ensures that the equipment which you are connected is also in a safe method. You can find all this information in NEC. So basically, NEC is a code of practice which is made mandatory. It talks about design, selection, erection and verification of an electrical installation to make electrically safe Bharat. So with this, I would like to stop the presentation. Thank you very much. I hope I could give some information to you. Thank you.